get to it then. So we are going to talk today about derivatives of logarithms. Last time we talked about logarithms, but actually not about their derivatives, just about what a logarithm means and doing sort of basic things with it. Today I want to talk about derivatives of logs. You know, I'm talking about like what is the derivative of the natural log of x, right? Or other logarithms. Remember, there's the natural logarithm, which is the log using the base of e, which is that special number for exponential functions. And then there's also just logarithms of other with other bases, right? And one thing is, you know, we have to remember these derivatives of logarithms are based on the exponential derivative formulas, which I hope you remember. These you have to use on the homework quite a bit. This is the formula for the derivative of a to the power x. It is a to the x times natural log of a. And then there's a special, nicer formula for e to the x. And it is, anybody remember this one? Derivative of e to the x is? E to the x is the answer. The nicest of the derivative formulas, because you get the same answer as what you started with. So these ones, you know, I suppose by next week you'll need to have these memorized. The second one is not so hard to remember. First one, you got to make sure everything goes where it goes. Anyway, what about the derivative of some logarithm? So what is derivative of some logarithm? This is a question. Like I said, this derivative, you can figure it out based on those two formulas in the box. Eventually, I'm going to write a formula for this and put it in a box. But to figure this out is not so hard to do using those two formulas here. So I'm going to say, sorry, my pen is acting up again. I got this fancy Apple pencil, but it doesn't really seem to have fixed it. I'm going to turn my iPad over and see if that helps at all. Here's how I'm going to say this. Let y be the natural log, not the natural log, the log, just some other log with base a. And then I'm going to take the derivative of that. So take the derivative, this is not what I meant. I'm not going to take the derivative, not just yet. If y is equal to the log with base a of x, this is a formula in the logarithmic form. I can rewrite this in the exponential form. So in the exponential form, this is something that we talked about doing last time at length. You rearrange everything so that it's not about a log anymore. It's about now something to some power equals something else. What's the base? It's going to be a, because a is the base of the logarithm. A to some power equals something. And just to fit this all in properly, it should say that. A to the y equals x. This is something we talked about last time. You can go back and forth. Whenever you see a logarithm, you can write it equivalently using an exponential function. And when you see an exponential function, you can write it equivalently in a logarithmic form. That is the exponential form of that thing. And now, here, I'm going to take the derivative on both sides. This is slightly weird what I'm doing here. Derivative on both sides. The right side, anybody remember anything? What's the derivative of x? This is the easy part. Nobody wants to say. Can you show me the fingers? This is something you can display on the fingers. It is 1. The derivative of x is always 1, so that's a 1 on the right side. What about on the left side? The derivative of a to the power y. Well, that, I scrolled the box, but it's this, right? Now this says a to the x, but I'm using y, but it's going to be the same idea. The derivative of a to the x is a to the x ln a. So what goes here is a to the y ln a. And then this is a little trick which I don't want to get into too much. I multiply times the derivative of y. That's because really of the chain rule. The formula in the box up there said a to the x. But if you have some different stuff on the inside of the exponent that's not x, in this case I have y, you have to additionally do the chain rule by multiplying by the derivative of the stuff on the inside, which is y in this case. This is a weird step, so it's not, and this is really the only time I'm ever going to do a step like this. So if that seems weird to you, don't worry about it. But it comes from the chain rule. Anyway, my goal is to figure out what is dy dx, so we can now solve for that. So I'm going to solve for this. You do that by dividing this other stuff onto the other side because it's all multiplied here. So it's going to say dy dx equals 1 over a to the y ln a. And then, finally, this will be the end of my little derivation here. You can see actually at the very top there, it says a to the y equals x. I'm going to plug that back into this formula. Because a to the y equals x, I could stick that right here. This a to the y is the same as x. And this is my final answer. This is the formula for the derivative of the log base a. So I'm going to write that just in summary. What I have just demonstrated is, so derivative of log base a of x is 1 over x natural log of a. This is the formula for the derivative of a logarithm. All right, not so difficult. I mean, it's not so complicated as far as formulas goes. And you just have to remember, this is what you get when you take the derivative of a logarithm. It is 1 over x times the natural log of a. Now, as usual, there is a nicer formula if it happens to be the natural logarithm. If it happens to be the natural log on the left side, what that means is, remember, ln of x uses the base e, right? Base e, the number e, right? So if I'm using the natural log, you're going to get the same formula, but this number a is actually e in that case. So that means the derivative of the natural log of x is, I'm writing the same thing, but the natural log uses the base e. So a in that formula up there turns into an e. It looks like that. If it happens to be the natural log, what you get is this. Anybody happen to remember what the natural log of e is? This is like a special thing about the number e. This is also something you can do on the fingers.
1.
It's 1. Yeah, if it's something convenient, probably the answer is either 1 or 0. This one is 1. The natural log of e is 1. And so what that means is this just straight up equals 1 over x. It's a very simple formula. So these, I'll put them both in a box. These are what you need to know about the derivative of, so the derivative of some log with some base is 1 over x ln a. And if you're lucky, it's the natural log. And that one has a nicer formula. It's just 1 over x. So these are the formulas for the derivatives of logarithms. They are pretty simple formulas. So once you know these formulas, you don't really have to remember all of this sort of derivation that I was just doing. These are the formulas. That, what I just said, is where they come from, but when it comes to actually using them, you don't need to think through all of that business. You just use the formulas. All right? So I want to do a bunch of examples, as we usually do, and then I got some for you all to try. Maybe I'll just move this guy over a little. How about, so here's some examples. Let's try the derivative of log base 7 of x. So this is very straightforward. You just plug directly into one of those formulas. Which one should I use? Well, is it a natural log or some other log? The answer is it is some other log. It is the log base 7. So I should use the first one here where a is 7. So this is just 1 over x natural log of 7. And remember that ln of 7 is just some number, which if you really want to know what that number is, you can plug ln 7 into your calculator. Although I almost never care about exactly what that number is. All right, that was a very simple just plug it in kind of example. How about, here's a more interesting one. How about the derivative of log base 4 of x squared plus 1? as usual, these formulas really are only interesting when they have other stuff around or inside of them. In this case, I am plugging some other thing inside of the log. And so we have to use the chain rule. That's what you always do when you have some thing inside of another thing. All right, so this is going to be a chain rule. I don't know what's up with the with my writing here. This is going to be the chain rule. So we do the derivative of the outer function, keeping the same thing on the inside, and then separately times the derivative of the inside. So what does that look like in this case? The derivative of the outer function is this log base 4. When I do the derivative of the outer function, I use this formula. So first I'm going to use this formula where it's going to say 1 over x ln a, but instead of a, I use 4, because that's the 4 here. And instead of x, I use this stuff here. So the first part of the chain rule looks like 1 over x squared plus 1 ln 4. All right, so what this, I'll put a little commentary here. What this part represents is the derivative of the outside. The outside is the log base 4 using a equals 4 and sort of x equals x squared plus 1. What I mean by that, this is weird looking, but what I mean is just this formula, instead of x, it's x squared plus 1, which is why right here I put x squared plus 1 rather than just x right here. Make sure you put these parentheses here. They are important. It means something different if you left those parentheses out, so don't leave them out. All right? Anyway, that is the derivative of the outside with the same stuff on the inside. That's why this is x squared plus 1. And then, because I'm doing the chain rule, I go times the derivative of the inside. The inside is just x squared plus 1, so the derivative of that is 2x. So this part here is derivative of the inside. That's the chain rule. All right, these can be a little confusing, in my opinion. I hope that seems all right. Any questions about that one? That's the chain rule with one of these. All right, I got 2 more, and then I have some for you all to try. How about the derivative of natural log 3x? Natural log is a little easier to handle just because the formula for the derivative of the natural log is easier to deal with. Remember, it was that, right? The derivative of the natural log of x is 1 over x. Again, we have to do the chain rule, though, because I have some stuff on the inside. So it looks, I suppose, vaguely like this one, although it's a little simpler. First, we do the derivative on the outside, which is the natural log. It turns into 1 over x, but instead of x, it's 3x. So the derivative of the outside part just looks like that. Because I'm using this formula, which is 1 over x, but it's 3x instead of just x, so it's 1 over 3x. That's the outside part, and then, because of the chain rule, I go times the derivative of the inside being just 3x. Can anyone say what's the derivative of that? Say it proud. 3, yes. I saw someone giving me the gang sign over there. 3 is the answer. That's the derivative of the inside. Excellent. All right, if you like, this can simplify. The 3's can cancel. Although it's 1 over x, actually. Although that doesn't really matter. All right, this is the derivative of a log. One more I got, and then I got some for you all. How about derivative of x times natural log x? This one is actually quite different from the other ones. You don't actually need a chain rule. The chain rule is what you do when you have some other weird stuff inside of a function. But inside the natural log here, we don't have any other funny business. It's just x. Can anyone say we have to do one of those other rules, though? Yeah? It is the product rule, she says. I agree, because there is a multiplication here, right? You know, it's like right there is a multiplication. It's x times natural log of x. So those are the 2 halves, or the 2 things which are being multiplied, and I got to do the product rule. And I hope you remember your product rule. It is the first thing like it is, which is x, times the derivative of the second thing. Derivative of ln x is 1 over x. And then plus the second thing like it is, that's ln x, times the derivative of the first thing. The first thing being x, the derivative of the first part is 1. So it's like that. And this is the answer here. If you like to simplify, x times 1 over x is 1, right? 1 plus ln x. That's how we do it. Sometimes you got to do the product rule. Sometimes you got to do the quotient rule. You can imagine if that was a fraction instead, you would have done the quotient rule rather than the product rule. All right. All right, I got some for you all. Let's see how we do. So find the derivative of each thing. Do I have to write that stuff? Log x. That's a very simple one. I got 4 here. I even tried to wash my screen. I thought maybe I had some like little dirty screen so I wasn't getting good contact. Didn't help. All right, see what you think. I'll come around and see how you're doing. Feel free to chat with your friends about it. Maybe I'll put the box of formulas back here.
You have to decide what's the A in this system. When you have a log and the base is not written, you assume that it's 10. This is just about So you do this, but you use A plus 10.
Okay.
And there should be X in that.
Okay, thank you.
Okay? That one should be the product. First part times during the second part, that's how all of this. Yeah, you can do all that stuff. And then you go plus.
So you could do
The card goes on, but it's the first time you heard it. Second thing, times another time. Okay? You have to do the product. Those are the right derivatives. You guys all right back here? Yeah, this one you have to do the product. Seems like you're trying to sound like
do the three.
So you gotta do the first thing times the second plus the
No. I'm just silly. Don't worry about it.
Doing okay?
You're doing the quotient.
Yeah. Yeah. You all good? Doing okay here?
Not quite. Yeah, you should be doing the product. This guy comes. This is a yeah. You should do two big things with plus it. Or sometimes with plus
Doing okay?
What is it, the derivative of the inside?
Yeah.
Is that
Yeah,
just the
the-
whole thing?
The outside is this log. The derivative of the log, so it's 1 over, work it out, so it's 1 over x.
Oh, that, okay, that would make sense.
Yeah, so it's 1 over x times. So in this case, that's x.
Okay.
Doing okay? Guys doing all right?
Yeah, this. Yeah, we messed it up, yeah. Yeah, it's the bottom times the derivative of the top. 2 to the x. So 2x, maybe refresh your memory. I wrote it through there.
Doing okay?
Okay, so thanks. Yeah.
How's it going?
Over the bottom screen.
Doing okay here?
Small comment. So it's 2, you get much harder. This is 2 to the power.
Doing all right?
That's like the,
That's only two.
So you could ask Ellen, like, for Ellen.
Yes. So I would suggest maybe try this one. This is a product.
Somebody else. It's so basically like if it's a to the x, it's the derivative is going to be a to the x times ln a. Okay, so the base, the natural log is always of the base.
How's it going?
Times ln
This looks good.
Okay,
x.
so this is the
Yeah, this one is paper.
it's always of that first.
But this is a multiplication. Whereas this is not a multiplication. It's a
Okay. I have to say it out loud or I won't. I knew she was gonna have it. I literally told you. It's gonna be Sam. Wait. It's just like
All right, can we talk about these? I see some people worked them all out, some people not so much. That's all right. So the first one I think is the easiest, provided you know what's up. A log with no base written. I didn't write any little number here. That means you assume the base is 10. That's called the common logarithm. And so for this one, I'm taking the derivative, of course. The derivative of that, I just immediately plug into this right here, and there's nothing else to it. This one, where I assume that a is 10. So this is just 1 over x ln of 10. So that is just verbatim plugging into this formula, using the base 10 because a log with no base written is always base 10. All right, the second one, that you must use the product rule. I'll bring it down here so I have some room. So the derivative of this thing, I use the product rule. The multiplication, of course, is right here, right? I have that thing at the beginning times the natural log of x. This, I don't know if you agree with me, sometimes this is the hardest thing about these problems, is just kind of, you have to be able to look at it and figure out what are my rules am I supposed to be using here? Or do I even need any of them? Sometimes you don't. That can be a little tricky to decide. In this case, it is overall a product of two things being multiplied together. And so I must do the product rule. And that, I hope you remember, it's the first thing like it is, times the derivative of the second thing, derivative of ln x is 1 over x. And then I go plus the second thing like it is, ln x times the derivative of the first thing, and that is 2x plus 3. So I hope that's what you got. All of those parentheses are important. When you have multiplications mixed with additions, it matters if you put the parentheses or not. So if you left them out, it does not mean the same thing, unfortunately. Any thoughts about that one? I hope this is what you got. As I was looking around, it seemed like people did okay with that. How about this one here? Now this one, perhaps deceptively, looks like it might be a product, but it's not a product. You might say, isn't this log 3 times that other thing? The answer is no. Log 3 is not a thing which you multiply. It's a function which you stick stuff inside of. So there is no product there. This is not a product rule. It is instead the chain rule because it's a function with some stuff on the inside. And so I'm going to do the chain rule using the rule about the log base a. So it's this one. Derivative of log base a x is 1 over x natural log a. So I'm doing the chain rule here where instead of a, it's 3, and instead of x, it's all of that stuff. I get 1 over all of that stuff times natural log 3. So that's using the formula on the right there, where instead of a, it's 3, and instead of x, it's all of that other stuff. And then because of the chain rule, now I have to additionally multiply times the derivative of that other stuff on the inside, which is 2x plus 3. That's my final answer. So this is a chain rule. It's not a product. I hope you got something like that. Any questions about that one? These, unfortunately, there are a lot of sort of little ins and outs, and it's easy to mess up a little piece of it. Okay, and then the last one. This one is a quotient. You can tell, usually quotient is easy to identify because it's a fraction, right? So you should do the quotient rule, which I hope you remember. This is the ho-de-hi thing. The bottom times the derivative of the top. Now the top is 2 to the power x. The derivative of 2 to the power x is 2 to the power x natural log of 2. This is the old rule. I wrote this rule at the very beginning of class. Derivative of a to the x is a to the x ln a. A lot of ins and outs. Anyway, that was the beginning of the quotient rule, right? The bottom times the derivative of the top, and now I go minus the top, like it is, 2 to the x, times the derivative of the bottom, and the derivative of ln 5x is 1 over 5x times 5. That's another little chain rule for the derivative of the bottom. Because when you have an ln, you just get 1 over whatever, but then you have to multiply times the derivative of the whatever. So I get 1 over 5x, and then times 5 is the derivative of the inside. And then I'm still doing the quotient rule all over the bottom squared, which you just write like that. This is my answer. Anybody got any thoughts about that? These can be easy to make little mistakes here and there, unfortunately. Yes?
Where do you get the 2 to the x times like ln2?
Here.
Yeah.
Yeah. This is derivative of the top. So that part, derivative of the top. And I used, for this, the formula derivative of a to the x is a to the x ln a.
Oh, okay.
Where in this case a is 2. So that's why it's 2 to the x ln 2. Yeah. Yes?
There's no need to put parentheses around the.
Here?
Yeah.
There is no need. Yeah, this is a good question. Why didn't I put parentheses like that? Actually, it's not wrong to put parentheses like that, so you can if you want to. It's not necessary because the only time the parentheses really matter is when you're mixing addition and multiplications. The reason is because, like, for example, 3 times 2 plus 1 is different from 3 times 2 plus 1 because of the order of operations, right? This first one will be 3 times 3, which is 9. The second one will be 3 times 2, which is 6 plus 1 is 7. So these are not the same, and it's because you're mixing additions and multiplications. If it's all multiplications, it doesn't matter because there's no distributive property for multiplication just with other multiplication. So, yeah, these parentheses don't matter because it's 3 things all multiplied. Right? This is like the stupid math memes that I see all the time. Because all the algorithms think that I like math, which is true, and so they give me these bogus, like, here's a problem that stumped the internet. And it's always some stupid order of operations thing. I'm not into the order of operations. All right. Great. One last thing to say about this, and then we'll move on to something completely different. So this is sort of a weird technicality that almost never matters, but it's going to come up later on in the semester, so I just want to mention it. I would like to note that what if I take the derivative of natural log of negative x? All right, this is very similar to things that we've done, just a few minutes ago. Like we just did ln of 5x, right? And this goes just the same way, except instead of 5, it's a negative 1, really. But anyway, it goes like 1 over negative x times negative 1, right? The 1 over negative x is from the formula for derivative of the natural log, and then this is the chain rule. You multiply times the derivative of the thing on the inside, which is negative 1. But these minus signs actually can sort of cancel, so this is actually the same as 1 over x. And we have this sort of weird, fun fact. So that means that the derivative of the natural log of x, of course, is 1 over x. And also the derivative of the natural log of minus x is also 1 over x, right? There's an extra dot there. That's not a minus or anything. All right? So what you notice is the derivative of a log is 1 over x, and it actually doesn't matter if the thing on the inside is x or if it's negative x, right? The sign on the inside has no effect on the answer, on the derivative, right? It's 1 over x either way, if it was x inside or minus x inside. This is not true of most functions, but for the natural log and for the other logarithms also, it is true. The sign on the inside has no effect on the derivative, all right? And what that means is, so actually, the derivative of the natural log of the absolute value of x is 1 over x. Remember, the absolute value just like throws away the sign. Whatever the sign is, positive or negative, it just turns it into positive. It ignores the sign. And so actually you get this weird formula, which I will put in a box. I wouldn't suggest that you memorize that. I mean, it almost never comes up. Like I said, I'm only mentioning this now because it's sort of a technicality, like several weeks into the future. I will say, hey, remember that time when I said that the log of the absolute value? You will say, no, I don't really remember that time, but this is that time when I say that. Maybe you will remember that there was a time when I said something like this. All right? The derivative of the log of the absolute value. And notice that over here in the answer, the absolute value is gone now, right? You don't also put the absolute value in the answer. And so the sort of short version of this is, so you should, this may come up on the homework, not on the test. You should ignore absolute values inside a logarithm when doing the derivative. All right. So for example, if I'm trying to do the derivative of, well, if it's just that, the answer is 1 over x, right? What about the derivative? Sorry, I gotta keep scrolling. Stay in the good zone. The derivative of, how about this? Natural log of x squared plus 3x. You can do this even with the chain rule or whatever. The big question on your mind should be, what am I supposed to do with the absolute value? And the answer is, you should just ignore the absolute value. It has no effect on anything. And so I do the chain rule as usual here. Because it's a natural log, I go 1 over x, but it's not x, it's that other stuff on the inside. X squared plus 3x. And then times the chain rule times the derivative of the inside, 2x plus 3. All right, you just ignore the absolute values entirely. This is the moral of the story. In my experience, this is actually what most sort of high school math students like to do with absolute values anyways. I don't like those, so I just ignore them. That's usually wrong, but in this case, it works just great. All right, that's my last little technicality about derivatives of a logarithm. And that's all that I wanted to say about derivatives of a logarithm. You'll have more practice on the homework. That's one of the topics on our checklist that'll be on the next test. All right. And actually, that's the end of a bunch of random formulas. I hope you don't mind. I recognize there's been like a lot of specific types of derivatives and formulas for them. We started off with the power rule, which is maybe the easiest of them, but then we had the product rule, the quotient rule, the chain rule, and then the derivative of exponential functions, and also the derivative of logarithm functions. And there are sort of formulas in boxes for all of those. This is it, though. There's not going to be any more of those kinds of rules and formulas to remember. Let's go on to something. So what we're going to talk about for the next month or so is going to be completely different, not based on new rules for new types of weird functions. What I would like to talk about for the next couple times probably is increasing and decreasing functions. This is a new chapter in the book too. This is chapter 5. I don't know if you care about that. Increasing and decreasing functions. Like I always say, like calculus is what you use to analyze how things are changing in the real world. And most of the time, one of the most sort of fundamental things that you care about as far as things changing is, are they increasing or are they decreasing? If you talk about changing populations or changing changing indicators in the economy or something like that, changing investments or business metrics or whatever, one of the most basic things you care about is inflation increasing or decreasing, or is the population increasing or decreasing, or whatever. Increasing and decreasing is a big deal. So the major kind of goal is, I give you a function, and you tell me when is that function increasing and when is that function decreasing. This is the basic idea of what we're going to talk about for the next little while. And first off, this, in my opinion, is easy to do if you can see a graph of the function. So this is, I will say, easy on a graph. So this is like a little warm-up, just so that we're clear on what we're trying to talk about here. On a graph, I could show you the graph of a function. How about something like colors? Just give me the red. Something like this, maybe. Say that's a function. Is the function in general increasing or decreasing? Well, the answer is sometimes this function is increasing and sometimes it's decreasing. For certain, remember, increasing means it's going up as you move left to right. So increasing, everybody knows this, I think, but I'll just write it down. Increasing means up and to the right. Equivalently down as you go left, but usually I think of the function as moving from the left to the right. Increasing means it's going up as you go to the right, and decreasing means it's going down as you go to the right. All right? And a typical function has like certain places where it's increasing and certain other places where it's decreasing. And you can see those on the picture. Like in this case, I would say in this zone right here, it's increasing. And then over here, it's decreasing again there. And then here it becomes increasing again. And then here it's decreasing again. And then here it's increasing again, right? If you're looking at the picture, this is always going to be easy to identify. When is it increasing versus decreasing? I hope you can see those colors. If I wanted to be very specific in asking you a question like this on a test, say, I would probably label the points a little bit more specifically. I would say, here's a bit of a more detailed example of a question like this. Sorry about that. Trying to draw straight lines, but they're not snapping. Let's go like this. How about that? So I tried to draw this fairly specifically. And if I want to ask you, when is this function increasing and when is it decreasing? If you are answering specifically, you would tell me there are certain x values for which the function is increasing, and there are certain x values for which it is decreasing. So the typical question that I would ask in this situation would be, give intervals of x values where it's increasing and decreasing. This is the only sensible way to answer a question about increasing and decreasing. For certain of the x values, it's going up, and for certain other x values, it's going down. And you just have to say which is which. I would say, for instance, my answer will be it's increasing for certain intervals and decreasing for certain other intervals. If we just look sort of from left to right, I would say over here it's increasing, right? And as an interval, this would be all the values that are to the left of x equals 1, right? That's how I tried to draw this. And as an interval, that would be, I would write that like this. The interval minus infinity to 1. And I'm always going to write these as open intervals. I'll just say a little bit in a moment about that. But for now, can we just write down what the intervals are? Minus infinity to 1. That indicates every point over here to the left of x equals 1. It's increasing because on those, the curve is going up. Don't be fooled by this little arrow pointing down. You might feel like, isn't that decreasing as I go like that? And the answer is, well, yeah, but when I say increasing, I always mean as you move to the right, it's going up. And that is true of this portion of the graph, even though there is a little arrow pointing downwards. Okay, what about the next interval that I see would be from 1 to 3, right? And along that interval, it is decreasing. So it is decreasing from 1 to 3. This is how I would say that. Now I'm not done yet. There's actually more intervals that I'm going to say here. But I have an increasing interval here, followed by a decreasing interval, followed by another increasing. This one now goes from 3 to 5. So it's also increasing here, 3 to 5. And then after that, to the right of 5, it's decreasing. That I would write as 5 to infinity is decreasing. All right. So these are intervals of the x values where the function is increasing or decreasing. I am only referring to x values here. These have nothing to do with the y values. I mean, it has to do with where the curve is going, but I'm not referring specifically to specific y values. All right. Any questions about what we just did here? In my opinion, this is fairly easy. You just look at the picture and then read off the intervals. You just have to remember, I'm talking about intervals of x values. So don't try and, like when you see this 3, 5, this doesn't mean x equals 3, y equals 5. It means all the x values from 3 to 5. Why am I using open intervals here? It's because technically we do not say it's, for instance, it's increasing from 3 to 5. But right on the end here at 5, it's not increasing. It's kind of neither at that point. It's not going up or down right there. And so 5 itself is not included as the increasing interval, and it's also not included in the decreasing part. All right. Okay, this, just looking at the picture, I think is usually pretty straightforward. What if I wanted to do this algebraically, that is only looking at an equation of something, this becomes quite a bit more involved, and that's what we're going to spend most of our time doing. Of course, you could graph it on your calculator if you had the luxury, but I'm going to, usually we want to do this sort of by hand. So how to do it, how to do this algebraically. All right, without looking at a picture. First of all, I would say you can identify where the intervals go. On the picture, I didn't make a big deal out of this before, but you can sort of focus, as we often do, on these bumpity bumps. Those bumpities are actually the x values which make the endpoints of the intervals, right? These are x equals 1, 3, and 5, and it's not a coincidence that 1, 3, and 5 appear down here. Those are the important points where it switches from being increasing to decreasing, all right? So the idea here, how do we do this algebraically? First, you find those bumpity bump points, and you can find them by, I would say you find all x with f prime of x equals 0. Those are those points. Those are the ones where the tangent line is horizontal, right? And actually there's a name for those in this context. These x's, these are called the critical numbers. The critical numbers. I like to say numbers. All right? Those are the numbers, the x values where the derivative equals 0. Okay? Why those are important? These are the endpoints of those intervals that you're looking for. All right? In the previous problem, they were like the 1, the 3, and the 5. If you know those, then actually you're well on your way to giving the intervals because you already know what the endpoints are. The only thing that remains is just to decide for each of those intervals, is it increasing or decreasing on each of the intervals? How do you know? Once you know these endpoints, you know what the intervals are. It's just how do you organize them into which ones are increasing versus which ones are decreasing. These are the endpoints of the intervals, and then we can check each interval and see the sign of f prime of x in that interval. The sign meaning positive or negative. And if it's positive, that means the function will be increasing. And if it's negative, that means the function will be decreasing. This is f prime of x, the derivative. So we can check each interval and see the sign of f prime of x. And I will just say positive means increasing because of the derivative is the rate of change. If that's positive, it means the thing is growing or increasing, and negative sign means decreasing. All right. So this actually, what you can see on the screen right now kind of describes the entire process. It's going to take you a few minutes to do each of these problems. You find all of the critical numbers first. Those make the endpoints of your intervals. And then you check the signs of the derivatives on the insides of those intervals to see if they're positive or negative. We're going to do a bunch of examples like this. All right? This is the setup, though. Let's see if we can try. How about f of x equals 3x squared minus 6x plus 8. The question is, where is it? Well, let me say more specifically. Give intervals where it's increasing and decreasing. This is always going to be the question for the next week or so. We're going to do a lot of problems like this. Give me intervals, it says intervals, where the function is increasing and decreasing. Okay, let's try and do what I said to do. The first step was find the critical Numbers. I saw this. I saw a 60 Minutes interview with a like a mafia hitman once, and he was talking about he was a hitman who then sort of betrayed his buddies, and the guy asked him, like, I thought in the mafia, like, nobody was a rat. You would never rat out your friends. And he says, no. I'm not a rat. A rat is somebody who turns in their friends secretly. I was a government informant, which means I testified publicly against these guys. That means he's not a rat. I didn't know this distinction, but he said these guys, we spend a lot of time together. They know where I live, so if they want to take me out, they can come and get me. But if they come and get me, they better come in numbers. This is why I always remember how he said this. Numbers. I like that. These are the critical numbers. This is my story about numbers. They better come in numbers. I don't think they ever came in numbers for this guy. I think he's still living his days out after killing several people. They let him off. The critical numbers, remember, they are where the derivative equals 0. Okay, so this is a bit of a process, but we need to find x where f prime of x equals 0. So we should take the derivative. First of all, this example, it's easy. Can anyone want to just rattle it off? What's the derivative here? Somebody shout it out. 6x minus 6, she said. I hope everybody remembers how to do the derivative of a polynomial. You multiply, the power rule, right? 2 times 3 is 6, so you go 6x, and then this negative 6x becomes negative 6, and the plus 8 at the end goes away because that's a constant. So this is f prime of x, okay? We are trying to find f prime of x equals 0. So I set this equal to 0. So I go 6x minus 6 equals 0 and solve for x. This is an easy one. This says 6x equals 6, x equals 1, all right? There is only one critical number in this example, and it is x equals 1. And this becomes, I guess, in this case, there's only one endpoint of those intervals. So what that means is the intervals in this case are minus infinity to 1 and 1 to infinity. There are no other endpoints. So it's just one side which is to the left of 1 and one side which is to the right of 1. There are no other critical numbers which make other intervals. All right? And now all that remains is to determine which one is increasing, which one is decreasing. Or maybe they're both increasing, or maybe whatever. But of the two intervals, are they increasing or are they decreasing? And for that, remember I said before, you need to check the signs. I actually like to make a little chart here. Let's make a chart of the signs. So I'm going to make a little, this is a very simple little chart here. What my chart is based on is, first of all, this is just a picture of like the real number line with 1 indicated, because 1 is my only important critical number. And it divides the entire line into two intervals. There's this one on the right, which is the interval 1 to infinity. And then there's this one on the left, which is the interval minus infinity to 1. So these are the x's that I'm talking about here. Those are the x's. And then what about the signs, f prime of x? Well, I can tell you one thing, it is 0 right there. That was the whole reason, like 1 is a critical number. What that means is that f prime of x is 0 at 1. What about over here and over here, though? What are the signs, be it positive or negative? All you got to do for that is plug in a single number over here and test it out and see if the derivative is positive or negative in that region. So anybody want to suggest, what's your favorite number in this region? That is x value which is bigger than 1. What do you think?
2.
Yes, I agree. You should say to something that's simple because I'm about to plug this number into the function. So don't choose, 18 because it's harder to plug in to the function. So I'm going to test x equals 2. So I go f prime of 2. I'm trying to test the derivative. And this f prime, you have to remember, I wrote it up there, is 6x minus 6. All right? When I plug 2 in, I get 6 times 2 minus 6. That's 12 minus 6, which is 6. Now, I don't actually care about that number. It's 6. All I care about is positive versus negative. But this one is positive. And so I'm going to put in my little chart here a big old plus right there. The derivative is positive to the right side of x equals 1. All right? And then what about on the other side? What's your favorite number to the left of 1 over here? You can have many favorite numbers, although there's one near and dear to my heart. 0, yeah, that's usually the easiest number to plug in, right? You're trying to choose some number which will be convenient to plug into this function. Now you can probably plug whatever you like, but 0 is certainly a good choice. So I'm also going to test x equals 0. I go f prime of 0 is 6 times 0 minus 6. 6 times 0 is 0, and then you subtract 6, I get negative 6, and this here is negative. All right, and so over there is a minus. And now we are done with the work of this problem. We can say now which of those intervals, remember we said before, these are the intervals, right? Negative infinity to 1 and 1 to infinity. Are they increasing or decreasing? We just figured out what the signs were. So I can say the increasing one is the one with the plus, which was 1 to infinity. And the decreasing one is the one with the minus, which is minus infinity to 1, like so. Sorry, this is a comma. All right. The increasing versus decreasing is according to those signs in the chart. All right. So can I just summarize this strategy here, and then we can do one more example, and then that'll probably do it for us. So the strategy here, if you like, first find f prime of x, set equal to 0, and then solve for x. These are the critical numbers. Wrecking the place. And they are important because they are the interval endpoints. That's why we care about them. All right? And then, so that's sort of the first step. Find the critical numbers. And then the second step is make a chart, plug in values to see increasing, well, I should say to see the signs of f prime on the intervals. This is the strategy. Maybe you could put that in a box. I don't know. If you like boxes. All right. This is how you find intervals where the function is increasing versus decreasing. All right, let's try another one. So the one that we just did was, I would consider sort of an easy one. A harder one can be quite a bit more involved. It was easy because we only had one critical number, and so there wasn't all that much to do. If you have more than one critical number, there can be more work to do. So let's try dish one here. X to the 4 plus 4x third plus 4x squared plus 1. How about that? And again, the question is, give me intervals for increasing and decreasing. Give intervals where it's increasing and decreasing. All right. I'm going to do the steps in the box. So the first step is find f prime of x, set it equal to 0, and solve for x. All right. f prime of x is, I do the derivative. Okay, this is a polynomial, so this is not so tricky. 4x cubed plus 12x squared plus 8x. And then the plus 1 goes away. All right, that's the derivative. Then set this equal to 0 and solve for x. So this is a little taxing in this example, but I think we can handle it. I go like so. Right? Set this equal to 0 and now solve for x. One thing I can do here to make this, I mean, you're going to have to factor here because you have a polynomial which is set equal to 0. One thing I can do to make this a little easier is to divide through everything by 4 because I don't like those big coefficients. Dividing everything through by 4 gives me x cubed plus 3x squared plus 2x equals 0. Yes?
Couldn't you just do 4x?
Yeah, I would also like to factor out x. You shouldn't actually divide the whole equation through by x because then you will lose some roots, but you should factor out the x. This is a good idea. Like so. If you divide by x, you will lose out on the root of x equals 0, which is important. So don't clear the x out entirely, but you can certainly factor x out like that. And then, I guess I want to continue factoring here. Can anyone see the factors of that part? Just considering this on its own. I'm going to keep x, but then this guy turns into that. What do you think? Any factoring masters out there? Yeah?
Would one of them be x plus 1, another x plus 2?
X plus 1 and x plus 2. Yes. She is a factoring master. All right. So now this thing is factored entirely, and we can solve for x by just setting each of the factors equal to 0. So I say x equals 0, or x plus 1 equals 0, or x plus 3 equals 0, right? And then each of those we solve for x. The first one is already x equals 0. The second one says x equals -1, and the last one says x equals -3. So I have 3 critical numbers. Am I doing all right? 3 different critical numbers in this case. All right? Great. Okay, so that's the end of like the first step, I suppose. It was kind of a lot of steps, but these are the critical numbers. Now I'm going to make my little chart here. Now it's important when you make your chart to, I have 3 points, right? And write them in the normal like numerical order. So -3 should be on the left, and then -1, and then 0, right? Because I'm trying to write, this represents a number line, and you better put those numbers in the proper order. Yeah.
Isn't the 3 negative 2
Oh, I said 2. Yeah. Sorry, I wrote 3 here, but she said 2. It should have been 2. Yes, she's the factoring master, not me. Sorry about that. I saw some puzzled looks, but nobody was going to object strongly. Okay, great. It should be -2. Thank you for that. Everybody feel better now about that? Okay, great. So -2, that means that number on my chart here should be -2, not -3. Thank you. Okay, great. Now, those are my x's. Now I need to plug the values, in between values, into the derivative. All right, so I'm going to do, just to make my chart here, f prime is 0 at each of those, right? Those are the places where the derivative is 0. That's the whole point of those numbers. They are the ones which make the derivative 0. I'm going to fill in between signs, pluses or minuses. And each of those is obtained by choosing a convenient number in between and then plugging that into the derivative. Now, in this case, the numbers are not terribly convenient. We need to choose numbers and plug in. Choose numbers in between, and then plug in to f prime of x. Now, here's a little pro tip. f prime of x, what was it? It was up here, right? I'm trying to plug into f prime of x, which is this. This, right? Now, this is a real pain to work with if you're going to be plugging numbers into this. I could plug 0 into this, but anything else I start to not want to do it. Plugging numbers into this is a real pain, but this is the same as this factored business, and that is actually much easier to plug into. So choose numbers in between, plug into f prime of x, and I'm going to use the factored form. And the factored form is f prime of x is 4x times x plus 1 times x plus 2. All right? It's just, it's this again. But I kind of resurrected the 4. The 4 came out, but sometimes that extra constant is important to remember. But anyway, this is what I'm going to use when I plug in, because I don't like plugging into some big polynomial, some weird numbers. All right. Anyway, what's it going to be? We got 8 minutes remaining. Let's choose a number. What do you say? A number to the left of -2? How about -3? That's my favorite number to the left of -2. Sorry, it's off the screen. You have to pick something for your first interval being over here, something less than -2. You might as well choose -3. What's it going to be? Plug into the factored version. This says 4 times -3 times -3 plus 1 times -3 plus 2. Now, you don't need to reach for your calculator to do these. All you got to check out is the signs of each of those pieces. The 4, of course, is positive. -3 is negative. What about -3 plus 1? That's -2, which is negative. And then -3 plus 2 is -1, which is also negative. Ugh. It's a struggle. Right? And so what is the answer? I don't want to deal with multiplying these numbers together, but I can say what the sign is, right? This is a positive times a negative times a negative times a negative. 3 product of, is the answer going to be positive or negative? The way to figure this out is, do you have an even number of negatives or an odd number of negatives? An even number of negatives will cancel and make a positive, but an odd number of negatives will stay a negative, right? So all of this together, 3 negatives makes a negative, all right? It is not necessary to, for instance, use your calculator to plug these numbers in, although you could do that and you would get the right answer, but you can't do that on the test. Just look at the signs of everything. Okay, so anyway, on my chart, this right here is a minus, right? The leftmost interval is a decreasing when it comes to writing the answer out. Okay, let's do the next interval, -2 to -1. Unfortunately, I have to choose like a fraction or a decimal in this case, but it's not going to be so bad. So I'm going to choose f prime of -1.5. That's in between -1 and -2. And again, I'm going to plug it in using the factored form. This is 4 times -1.5 times -1.5 plus 1 times -1.5 plus 2. I'm using this formula up here. Maybe I'll put it in a blue box. No. In a blue box. I'm plugging in -1.5 to the formula in the blue box. All right? And then, what about those? The signs of each of those parts? All right, I got 4 is positive. -1.5 is negative. -1.5 plus 1 is -0.5, which is still negative. -1.5 plus 2 is positive 0.5, which is positive. And so this whole thing is positive. It's 2 negatives in there. An even number of negatives makes it positive. Yeah?
After we found the first negative, could you assume that the next one's positive and then the one after that is negative?
This is an excellent question, which I'm sure all of you would have found yourself wondering eventually. Aren't the signs always just going to alternate, negative and then positive and then negative? The answer is no. They don't always alternate. To be honest, they usually do, but not always. So you really do have to check the various things. The reason they usually alternate is because most functions, they go sort of up and down and up and down. Although sometimes it is possible for a function to do this and then continue going up, even though its derivative is 0 here, but it's up and then up some more. So it can be non-alternating, unfortunately. All right, can we do 2 more in our remaining 4 minutes? Do you remember when I said these can kind of take a long time to do these problems? I'm feeling it right now. So in between -1 and 0, I'm going to choose -1/2 or -0.5 if you like. So I'm doing f of -0.5. Again, plugging into the formula in the blue box. 4 times -0.5 times whoa. Put me in text mode. I never want that. -0.5 plus 1, -0.5 plus 2. All right, what do I got for positives, negatives? That's positive, negative. -0.5 plus 1 is positive 0.5, and then -0.5 plus 2 is positive 1.5. So this all ends up being negative. I got 1 minus in there, so it's a negative. So this on my chart is a negative. And then finally, this one's easier. A number to the right of x equals 0, I'm going to choose x equals 1 and plug that in. So this is the last one. F prime of 1 is 4 times 1 times 1 plus 1 times 1 plus 2. These are all positive, 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 which means the whole thing is positive. So this is positive over here. All right. And finally, my final answer, remember the whole thing here is to give me the intervals where it's increasing versus decreasing. So my final answer then is increasing on the intervals. What are the plus intervals? -2 to -1, that's a plus. And also 0 to infinity. Those are the 2 pluses, right? And I write them down as the intervals of x values. -2 to -1 and 0 to infinity. And then it's decreasing from -infinity to -2 and also -1 to 0. This is my true final answer. All right, maybe I'll put that at the bottom. There you go. That'll do it.